2015 question number 4 starts by giving us a differential equation or just the first derivative in most cases. And part A is asking us to sketch a slope field at the 6 indicated points. So overall, here's how your setup will look on the test. You'll be giving some sort of graph that looks like this, a y-axis and an x-axis, and here are your 6 points. Now, to plot a slope field, you literally just plug in the points into your differential equation, and depending on what value it gives you, positive or negative, high or low, that will determine if it's a slope that's upward or down sloping and by how much. So let's look at perhaps the axis x equals 0, right? When x equals 0, I can just ignore this first part here, this 2x part. So I'm only going to focus on my negative y. When I plug in negative 1 into y here, right, this point, 0, negative 1, 0 for x, but negative 1 for negative y, this makes it into a positive 1 slope. Because again, the 0 canceled out the 2, and allowed for the negative 1, but my y here is already negative, so that's this positive 1. So a moderately steep slope that's upward sloping. Now when I go up to the positive area for my y values, my x is still 0, right? I'm plugging in 0, 1 or 0, 2, but this time my 1 is positive, so I'm going to take this 1 and put it in here, and this actually becomes a negative 1. So downward sloping, moderate, steep. And same thing here, 2 goes into negative y, again at the point 0, 2, so 0 for x, and this becomes also downward sloping but a little bit more steeper. Now moving on to this side, here my y is 1, my x is 1, my y is 2. This is essentially going to cancel out to 0, so I'm going to have a flat slope like this, a slope of 0 in that sense. Not positive, not negative, just 0. And here you can fill out the rest. This will be a positive 1 slope. This will be the steepest positive 3 slope. So that's how your slope field will look like. This question is worth 2 points. 1 point for all your slope fields on the x equals 0 vertical line, and those at x equals 1 vertical line as well, at your 6 points. Part B is asking us to find the second derivative, right, in terms of x and y, and to determine the concavity of all the solution curves in quadrant 2. So we're going to take this equation here, this first derivative, and we're going to differentiate again. But you'll see here, as I move these sticky notes out of the way, that you're going to be differentiating with respect to x. So what you have here is really important. Dx here, this is very similar to implicit differentiation, what you've done before. So I have an x here, but I have a y here. So that means when I take the derivative of this, I'm essentially going to get 2x, or just 2 here, because 2 is in terms of x. But when I take the derivative of y with respect to x, I'm going to get dy dx. I'm keeping the signs the same. So my second derivative so far looks like 2 minus dy dx. Well, you may stop there and wonder, what do I do from there now? How do I evaluate or plug in points? Well, you can see here, it's just all about really taking in what you've seen before. I'm going to take this dy dx and substitute with this dy dx. So now, I'm essentially going to plug this entire first equation into here, and I get something that looks like this. You distribute, you make it prettier, and you get something that finally looks like this. And my reason, of course, was that in the second quadrant, all my x values are negative, and I'm here, there's a negative 2x, so that's going to be positive, making all my x values. And my y value is also positive, so in all cases, my solution curves would be concave up, because again, this is second derivative. But again, you could probably say it in a different way. You just understand that in the second quadrant, your x values are negative, but your y values are positive, and that fits nicely with this equation. Another 2-point question, 1 point for getting the second derivative here, not just dy dx, because before, they are specifically in terms of x and y. So that's why here, we had to substitute this first derivative into here, and get our second derivative in terms of x and y. And 1 point for the answer with the reason. Part C wants us to evaluate this function f of x with a particular condition, f of 2 is equal to 3, and it wants us to see if it's a relative maximum or minimum or neither at x equals 2. But at x equals 2, we get 3. So literally, you're just going to plug in to what you have here. You plug into this equation, right? The equation you're plugging in for 2, 3 is here and here. And when you do that, you realize that dy dx evaluated at 2, 3 is 1, which is not equal to 0. And after the side, you can after the side, you can see that I say that for it to be your function to be a relative maximum or minimum, the first derivative has to equal 0 and has to change signs. In this case, dy dx, or my first derivative, does not equal 0. So therefore, it's neither a maximum or a minimum at x equals 2. So, but all you had to do there was simply plug in 2, 3 for x and y respectively, and then notice that that did not give you 0, right? Definition of a critical point. And then instead just state that it was neither a minimum or a maximum. 2 points in total, answer with reason, and evaluating dy dx at x equals 2. Last part. Now this one was actually pretty tricky. We wanted us to find the constant values, m and b, for y equals mx plus b for this particular solution, right? Well, where do we even start? First off, you just have to write down your equations. Given this equation, y equals mx plus b, the equation of the line, and you have to understand that dy dx is the slope here. So this slope here, m, you may remember from your algebra class, is just the slope. Well, what's another name for the slope? The slope is the first derivative. You can also do that by literally differentiating dy with respect to x. Mx would go to just m, and b is just treated as a constant, so that just goes to 0. So if you were to differentiate this line of the equation of the line, you would get dy dx is equal to m. Or you can just remember from your algebra class that m is equal to your slope, and again in calculus your first derivative is your slope at a point. Now again, this is all just like the last one, right? Just like before when we were to find the second derivative and we connected 2 and we substituted, you're going to do the same thing here. You realize that dy dx is equal to 2x minus y, that equation that they give us at the beginning. So from there, because these two are the same, I'm going to set them equal to each other. And I get something that looks like m is equal to 2x minus y. Now we're into another question. Now I run into another issue. I have an x variable, but I have another variable, and that's too many unknowns. So I'm going to take this y value here and substitute my mx plus b. It's all about substitution and using what you've used in the past, right? This y value here goes here. Well, again, I literally substitute. M is equal to 2x minus mx plus b. Rearrange it, make it pretty. And you see here I get, when I factor out this x here, when I factor by grouping, I get 2 minus mx minus b. Well, this is a variable, right? And this is a constant. So I'm going to treat this as if it was a 0x, implied as if it was nothing there. A 0x and an m here, my m is my constant. You can see now then that if I were to match my like terms, my x here, x is over here. So 2 minus m is equal to 0, matching my terms x and x, or m is equal to 2. And finally, matching my coefficients, or just my constants, here and here, I see b is equal to, m is equal to negative b. So overall, m would equal 2, and b would equal negative 2. This question was very tricky, but it's worth 3 points. 1 point for saying that the first derivative is equal to your m slope. Another point for saying that your equation from before, dy dx, is equal to that m. So just 2 points just without doing any math. And then 1 point for the actual answer itself.